Yes, some kind of guy. Let's talk about PAAL KNOR synthesis. PAAL KNOR synthesis is a classical organic chemistry a reaction which involves cyclization of a 1,4-dicarbonyl compound to form five-membered aromatic heterocyclics. These are furan, Thiophene, and pyrrole. So, in this video, we are going to talk about PAAL KNOR synthesis. And this is the compound we are talking about. Ketone, one is in position 1, then this is 2, 3, and 4. So they are in 1 and 40 positions. So these other groups can change. They can be any compounds or any substituents. But when you look at the compound, it is 1, 2, 3, 4. So it is 1,4-dicarbonyl. So this is furan, and this is pyrrole, this is Thiophene. We are also going to talk about these three other reactions. We are going to see, because here we are putting an acid, we get furan, but when you put a base, we get this compound. How are we going to synthesize it? We are going to see the mechanisms for all. Then, how would we form oxazo? This is isoxazo, and this reaction can also lead us to isoxazo. So we are going to talk about all the mechanisms of these reactions. Let's begin. If you have a 1,4-dicarbonyl compound in presence of weak acid, for example, acetic acid, or some traces of HCl, you can get furan. How do we begin the mechanism? This compound, for simplicity, you can draw it in this way. It's the same compound. So we can draw like this. You put your R1, R2, then these are the two keto groups. So I saying you haven't done anything, but it's almost similar to the product. So then acid, the proton, remember these oxygens, they have lone pairs of electrons. So one oxygen can attack the proton. Then we form this R1, then you're having oxygen with a hydrogen. So it's now positively charged. Yeah, there is R2. This is what you are having. Now, this oxygen to stabilize, it will try to break this bond to stabilize. When it breaks the bond, this carbon will become unstable. So it's a carbocation. Remember, we are having here hydrogen ions. The carbon is saturated. So one of the bond will break and form a bond here. So we shall have this. And these reactions are reversible. So we shall have this with oxygen. It's now OH group, R2. Then we have formed a bond here. And we're having this with R1. This is what we are having. Now, this one is also having lone pairs of electrons to attack the acid. As it attacks the acid, we shall form this. Here we're having OH, it's OH, then having this with hydrogens. Now a plus, then R2 and R1. So R1, it's a plus. Now, it will pull electrons toward itself such that it stabilizes. When it tries to do so, this oxygen will attack this carbocation which is formed. So we shall have this. Oxygen has closed now the ring, but it's having hydrogen, so it is positively charged. And we're having OH now. This oxygen has stabilized R1 and R2. Here we shall have a proton shift. So this hydrogen will shift to this oxygen such that this one stabilizes. So we're having O, then OH2. This one now positively charged, R2 and R1. I see. So remember, this oxygen is having lone pairs of electrons. When it forms a bond here, this one will break off. When it breaks off, shall form this O with a double bond. It's now plus R1, R2, and you're having a bond here. So remember, hydrogen here, this carbon is still saturated. So when oxygen pulls electrons back to stabilize, one of the bond will break, form a bond there. So we shall form this R1, R2. So this is our furan. Remember, these are groups. It can be hydrogen, it can be a phenyl group, it can be any group. So we're having furan. These are substituents. That's how we form furan. So if you just add acid, you get furan. But if you put acid with another base, or this is amine, this is hydrogen sulfide. If you put amine, we get pyrrole. If you put hydrogen sulfide, we get Thiophene. Let's also these mechanisms. Yes, for this mechanism, we are having a primary amine. Here we can use a primary amine or ammonia. We can use primary amine or ammonia for this reaction, but is acid catalyzed. We are having acid. Sometimes it can be in a neutral pH. Now let's see the mechanism. We are having this R2 and R1. We are having a proton. Oxygen will attack the proton. When it attacks the proton, we shall have this R1, R2. Then here we are having O with H, but this one is now a plus. So when it pulls electrons to stabilize, this amine, the primary amine, will now come. Remember, nitrogen is having lone pair of electrons to attack this carbocation. So we shall form this with R1, oxygen, R2, then you're having OH. You're having OH with N, hydrogen, another hydrogen, and R group, but it's now positively charged. It's positively charged. So here we shall have proton shift. Remember, in the imine, we saw the mechanism about formation of imine. So same principle applies here. Same principle. R1, oxygen, then here we shall have a proton shift. So we shall have OH2. It's now plus R2, then N with H and R. That's what we are having. Nitrogen has gained its lone pairs of electrons, so it will form a bond. As it forms a bond, this one breaks off, so we shall form this R1 oxygen, R2 amine has formed double bond, so it is N, H and R. This is what we are having, and it's now a positively charged. So remember, we're having hydrogen here. This carbon is saturated. So as this one tries to stabilize, to pull electrons, these bond electrons, creating a carbocation, making this hydrogen to lose bond electrons form here, a bond. So we shall have this a bond N with a hydrogen and R group. This is R2. So let's name this one R3 under nitrogen, such that we are not confused. R3, it's R3. Then having oxygen and R1. This is what we are having. Remember, this oxygen is electropositive. I mean, it's electronegative, and it will attack a proton. As it attacks the proton, we shall have this R1 O with hydrogen, it's plus now. R2, then we're having N, H, and R. This. So it will try to stabilize with electrons towards itself, creating a carbocation. This nitrogen will attack the carbocation. So we shall have that. R1, you have created OH group here, then N with hydrogen and R3, then R2 here, and a double bond. You're having this double bond here. Don't forget. So nitrogen is now positively charged. It's positively charged. We shall have a proton shift. This hydrogen will go to this oxygen, forming this R1 N with R3. Then we have R2 there, a double bond, and OH2. It's now plus. So nitrogen forms a bond. This one breaks off, forming this R3, R1, then N with a double bond here, and charge R3 down. Remember, it's now positively charged. Here, this carbon is still saturated. As nitrogen pulls electrons back to stabilize, this hydrogen loses electrons, form a bond. So we are losing a proton there. So we form this, a double bond here, then N with R. So we have R2 here and R1. So this is our pyrrole. This R, this R can be hydrogen. Remember, we said it can be primary amine or ammonia. So if it's hydrogen, it is ammonia. So this is our pyrrole. In case this is hydrogen. Yes, for Thiophene, in laboratory, Thiophene is synthesized using phosphorus pentachloride, pentasulfide, phosphorus sulfide, which is P4S10, this one. Or Lawson's reagent. They don't use hydrogen sulfide, but theoretically you are going to use hydrogen sulfide, but in laboratory most times they use this reagent due to some critical reasons. So now hydrogen sulfide and the 1,4-dicarbonyl compound, having this acid catalyzed. You have our acid. Oxygen is having lone pairs of electrons. So we shall form this. This is R1, this is R2, this is R1, we are having R2, and here we have formed this. It's now plus. So as it stabilizes, it pulls electrons towards itself, the SH group is H2. This one attacks the carbocation formed. So we are having this R2 and SH2. It's now plus. Then R1 with and OH. That. Then here we shall have proton shift. Proton shift forming this SH R2 and OH2. It's now plus. Sulfur is having lone pairs of electrons, so it attacks this carbocation and this one breaks off, forming this R2, R1, oxygen here. Then we have formed SH with a double bond. Now plus, and we have lost water, so you can put here minus water. Then remember here hydrogen and another hydrogen. This carbon is saturated. This one tries to stabilize, then we form a bond here. So we shall form this SH. We have lost our hydrogen, so we form a double bond. We have R2, then R1 with oxygen atom. This one also attacks the acid. So it takes the proton. As it takes the proton, we shall form an ion, which is O with hydrogen and it's having a plus. You have R1 here, R2, and SH with a bond here. So as this one stabilizes, it pulls electrons, the bond electrons, creating a carbocation. Sulfur attacks the carbocation, forming this R1. Then we're having S has closed the ring with a hydrogen, but it's now plus. Then we're having OH group, and here R2 with a double bond. We shall have proton shift. Proton shift. This hydrogen will go to oxygen, forming this. Here we're having S and OH2. It's now plus. R1, don't forget, R2, a double bond. So sulfur is having lone pairs or electrons. It forms a bond, then this one breaks off, forming this sulfur. A double bond here, it's now plus, we have R1 and R2. We have lost another water, so minus water. And a bond there. Now, as it tries to stabilize, remember, this one is still saturated. One of the hydrogen will be lost, forming this R2, R1, S with two bonds. So, if these are, they are both hydrogens, we are having Thiophene without substituents. But if these are other groups, so it is Thiophene with two substituents. That's how we write the mechanism for this reaction for synthesis of Thiophene. So these three mechanisms, they are known as PAAL KNOR synthesis mechanisms. We form the furan, Thiophene, and pyrrole, which are aromatic heterocyclics and 5-membered. Let's talk about these three mechanisms also. Yes, same the guy. Let's talk about this reaction. We have seen using this compound, we can synthesize the aromatic heterocyclics, these three. But here, when you add a base, you're forming this compound. And also, remember previously, when we were starting this video of synthesis, we talked about reaction of the OH group or a base with a ketone. So we are going to use the same principles to synthesize this compound or to write the mechanism. Here we go. We're having this. That's what we are having. Remember, we said that this nucleophile will attack the alpha carbon. This is the ketone group. This is the alpha carbon. This methyl group is having hydrogen, hydrogen, and hydrogen. So this one will act as a nucleophile, attacking one of the hydrogen. And this hydrogen will lose the bond electrons to the carbon. Let's write it like this, so that it can be visible to the carbon. So we shall form this oxygen, oxygen, and we have created a nucleophile there. So we can have resonance. This oxygen is electron negative. Then this one forms a bond here, as we have seen in previous videos. So this is reversible. We form this. This O is O minus. Then we have formed a bond here. Or you can write like this. Oxygen this side. Then you have formed a double bond here. There. As this oxygen pulls electrons towards south, this one forms a bond here, and this one attacks the carbocation. As this forms a bond, this bond will break, creating a nucleophile here. This one attacks the carbocation formed after oxygen pulling electron towards south. So forming this. Then this is O minus. This one has closed the ring now. And this oxygen is here, like this. Like this. This oxygen can get hydrogen from water. So can have this with O, and can attack, of course, can attack another water until it gets to hydrogen, two hydrogens forming O plus. It gets one, then it remains with lone pairs, it attacks another water, so we form this. Here we're having ketone. Remember, here we have hydrogen, also here we're having hydrogen. It is saturated. As this one breaks, one of the hydrogen forms a bond here. So we shall have this with a bond here and a keto group here. So this is position 1. This is 1, 2, 3. So it is 3-methyl cyclopentanone. Pentanone. It is alkene. So that's the product. When you put OH group in 1,4-dicarbonyl compound, this is the mechanism. How can we form this heterocyclic? This is isoxaz with acetyl group and a methyl group. Let's write this mechanism also. We're having this reaction of isoxazole formation. You have this. Another keto group here. Then N, double bond, and OH. This is what we are having. Then we're having a proton acts as a catalyst. This oxygen is having lone pairs of electrons. It will attack the acid. So we shall form this O with H. It's now positively charged. Then we're having our OH group. This is oxygen. This is oxygen. In presence of an acid, you are forming isoxazole. So here, this is what you are having. As this one pulls electrons to stabilize, remember this oxygen is having also lone pairs of electrons to attack the carbocation formed. So we shall form this. This one will now be OH group. Then you're having N with oxygen, and it has formed a proton. Now here we shall have proton shift. This hydrogen will go to this oxygen. So we shall have this N with now this oxygen and OH2. This one is now positively charged. This oxygen, remember, it has lone pairs of electrons. It forms a bond. This one breaks off. So we form this N with O like that and a double bond. This one is positively charged. We have lost water. We have lost this water. Now here, remember, this carbon is saturated. We are having 2 hydrogen ions. As this oxygen regains stability, one of the hydrogen is lost from a bond here. So we have this N or this oxygen, and we have formed a bond here. So with O, that's it. So that is our isoxazole. Remember, this is position 1, 2, 3, 4, and 5. So it is 3 acetyl, 5 methyl oxazole, 5 methyl isoxazole. So that's our product. We are seeing here, we can have this mechanism leading us to same product, but also here we are having this can give us same product. Remember, this is oxygen. This is oxygen. Let's see whether from this we can form this. How is the mechanism? Yes, for this reaction, this one must be a stronger acid reacting with this weak acid such that we can form this product. So if you have nitrous acid, this nitrous acid with OH like this, plus another acid, we shall form this OH2 plus with N like this. So we shall lose this as water, forming this as electrophile. So we're having this as an electrophile. So for our mechanism, we are having this a diketone like this. Remember, from previous mechanisms, we saw that this oxygen is electronegative. It pulls electrons towards itself. You can have resonance. Here we're having hydrogen and another hydrogen. So as it pulls electrons, one of them can be lost. Form this. It's a resonance reaction. So we're having O minus, and we have formed a bond there. This is what you're having with oxygen here. So as oxygen comes back to regain stability, this one will now attack the electrophile. This electrophile. So we're having this O, then we're having N with oxygen like that. Now here, this oxygen can attack a proton again to form this NO plus now, and this is what you're having. So it is unstable. It is unstable. So as it pulls electrons form to stabilize, remember here we're having a hydrogen. This hydrogen will be lost to form a bond with nitrogen, forming this. Now we're having a double bond with N and OH. So this product we are having, it is oxygen, and it's the same product here. So meaning that when you reach here, the same mechanism goes and takes you to the product, which is isoxazole, after getting the oxygen. So you continue with the other mechanism we have done. So that's all about pyrrole and these other three mechanisms. Now we are going to talk about the Knorr mechanism. This guy without the PAAL also did these reactions. And also we talk about the Hershey-Widman synthesis. Thanks so much. Same the guy. Please don't forget to subscribe, like the videos, and share. Thanks so much.